In this problem, we're going to determine whether these vector fields are conservative. And because they are three-dimensional, we don't have that condition of checking with the mixed partials. Remember that if you can show that partial p partial y equals partial q partial x, then what that shows is that by equality of mixed partials for a two-dimensional vector field, then it must have descended from some original scalar function. For 3 dimensions, you have a more complicated condition to check, and it's that the curl of the vector field is the 0 vector. Now, if we are able to show that one of these or both of these have a 0 curl vector, then we have the additional task of finding a potential function such that this vector field is the gradient of that. But we'll cross that bridge when we get to it. So part A, we do have 2 problems to do here. Let's say we'll take the curl of this. The curl of a vector field equals the del operator cross the vector field itself. This is a messy and difficult process, but there's only one way to do it, and that is to just go and do it. So the I, the j, and the k components. Then you write the partials. So partial with respect to x, partial with respect to y, and partial with respect to z. And then the components of the f, the actual vector field. This will be e to the z as the I component. The j component is simply the number 1. And the k component is x e to the z. It seems to me like f equals x times e to the z would work here. Because if you take the derivative with respect to x, the x drops out and you're left with e to the z. Take the derivative with respect to y, and well, actually, hang on. Maybe if you include plus y at the end, then the derivative with respect to x will make that drop out. Derivative with respect to z will make it drop out, but derivative with respect to y will cause the constant of x e to the z to turn into 0, but the y will turn into 1. So I think that this is a good candidate. We should expect that this is going to be conservative and that this f will work, but let's watch the process anyway. Okay, cross product goes like this. We're going to take I component is this minus this. So we're going to take partial derivative with respect to y of x e to the z. That's 0, nothing at all. Minus the partial derivative of 1 with respect to z. That is 0 for the I component. Cross product is a determinant which switches to minus. So now we're going to be taking, as the j component, it'll be this minus this. So partial derivative with respect to x of x e to the z, this is e to the z. And partial derivative of e to the z with respect to z is e to the z, e to the z as well. So just to emphasize, this is e to the z minus e to the z. As the j component, e to the z minus e to the z, of course, is 0. Now you switch again back to plus for the k component, and this will be partial derivative of 1 with respect to x, which is 0, minus partial derivative of e to the z with respect to y, which again is 0. So this is just identically 0. So because the curl is 0 here, yes, it is conservative. You do have to go and find, though, what scalar field does this descend from? So like answering the question of is it conservative is different. It opens a gateway to answering the second question of what does it come from? What's the scalar function? But it doesn't answer the question itself. I think we can just say like f of x, y, and z. It's a little bit obvious that it's going to be x e to the z plus y. And this is because in that situation, partial f partial x would be what? Well, it would be e to the z, wouldn't it? And partial f partial y would be 1 partial f partial z would be xe to the z. And like all these constructive methods where you go and you find the answer, yeah, those are all well and good. But if you can just pick it out and demonstrate that it works, then don't feel the need to go through and say, here's how you follow the steps. No, if you can see the answer, you're already good. Okay, so we're done with that one. Let's do the second one. I just love doing cross products, don't you? Okay, time for the second one, in which case I'll switch to a different color. So the same thing as before. We want to show whether the curl of this vector field equals 0 identically. So let's go get the curl. The curl is equal to the del operator cross f, which is I, j, and k, partial with respect to x, y, and z, and then the components of the vector field itself, the y cosine xy, x cosine xy, and negative sine of z. When I get part of the way through writing a cross product, I always realize I didn't give myself enough room on the final row. Oh, well. So the usual way of computing this is the I component is this minus this. Partial derivative of negative sine z with respect to y, 0. Partial derivative with respect to z of x cosine xy, yeah, it's a scary looking function, but this is z. Z doesn't show up here. So those are both just 0. Boom, identically. So this is 0, I. All right, so far so good. Minus, and then for the j component, it's going to be this minus this. Once again, the same sort of thing is going to happen. We're going to differentiate with respect to x with a function that has no x's, and then differentiate with respect to z with a function that has no z's. So this is going to be, guess what? Big fat goose egg. 0j. Let's see if we win the last one as well. For the k component, it's going to be partial derivative with respect to x of this minus partial derivative with respect to y of this. We hopefully will end up with some symmetry here. This is our first derivative that's not just going to be boom, 0. So let's see. Plus, okay, what is the partial derivative with respect to x of this? It's product rule. So it'll be like f prime g, the derivative of the first times the second. That'll be 1 times cosine xy. And then plus the derivative of the second times the first. Because the derivative of the second is going to be minus sine, it will be subtraction. It'll end up being subtraction. And this will be minus x times sine of xy. And let's see, sine of xy. If we're differentiating with respect to x, then the y comes out because of the chain rule. So this really is xy, sine xy, right? Okay, so that is the first differentiation here. Now we're going to do minus this differentiation here. Okay, no big deal. Minus, and let's use some more brackets, differentiate that with respect to y. This is the same question. It's just that the x and the y have switched places. They're both still on the inside, but now the y is on the outside. So I'm going to do everything with y's that I did with x's before. Sound good? So I'm going to say this will be cosine of xy minus, minus xy sine xy. Okay, now is when I get the payoff to see if they cancel out. For the other ones, they were very easily identically 0. This one, we just got to put in some legwork. So cosine xy, that's non-zero, but it is minus cosine xy here. So those go away. Then negative xy sine xy minus negative xy sine xy. Bingo, they match. And so they're gone as well. So this is 0k. this clinches it. We've seen that this actually is a conservative vector field. Now, let's see, can we guess what this one is, like the same way that we did before? A little tougher because there's like so many moving parts. This part indicates that there's probably going to be a plus cosine z at the end, because a plus cosine z will differentiate into a negative sine z. The rest of it's going to be x's and y's, because the x's and the y's would be what generate these things right here. So can we guess it? Yeah, I think we can. What if it's sine xy plus cosine of z? So let's say f of x, y, and z equals sine xy plus cosine of z. Let's see. Partial f, partial x. The cosine z part obviously goes away. And for the sine xy part, it's just going to be chain rule of y times cosine of xy. Does this line up with the I component? Yeah, it does. Y cosine xy. Boom. I'm pretty sure this is going to be a winner. Partial f, partial y. This will just be the same thing, except y comes out now. I'm sorry, x comes out now. X times cosine xy, which does line up with this. And then if we take the derivative of f with respect to z, this is the only time that the cosine z part is not simply a constant. So everything else is a constant, but the partial derivative with respect to z is negative sine z, which is exactly what we need based on up here. So we see that once again, this is conservative, and this right here is the potential function that makes it happen. I hope it doesn't bother you that I took like a non-constructive approach to choosing the potential function this time. I think it's useful to be able to backtrack kind of mentally. It's almost like a form of mental math, which can come in really handy sometimes.